Motion in a straight line. Chapter 2. So, what is straight line motion? Well, it's any movement that is in a straight line, like left to right, up or down, diagonal, but it cannot be a curved or irregular path. So, this is usually called maybe even one-dimensional motion. And now we're dealing with mechanics, that study of objects, classical mechanics in fact. So we've got statics and dynamics, objects at rest and objects at motion. And then in dynamics, kinetic and kinematics. Kinetics deals with the laws of motion, like first law, second law, third law. Kinematics, on the other hand, deals with the motion itself, like what is the acceleration, what is the velocity, what is the distance, what's the displacement, without going into the reason why this motion has occurred, so we won't be working with forces under kinematics. Now, what is distance and displacement, and what are their differences? First of all, we need to know what's a scalar and a vector. A scalar only has a magnitude, example 5 meters. A vector, on the other hand, has a magnitude as well as a direction. So for example, I'll give 5 meters and in some direction, like 30 degrees east of north, or 30 degrees to the left, so some indication of a direction. So just think about an arrowhead. Now we have two important vectors that come about, position vectors and displacement vectors. A position vector is defined as the vector from the origin to the position of the object in a coordinate plane. So it points from the origin to the object where it is. Simple. Displacement vector is the vector between the initial position and the final position of the object. So it's actually you can just subtract the position vectors to get the displacement vector. That's RF minus RI is equal to delta R, where delta R is the displacement vector. Now displacement vector is equivalent to displacement because displacement is the change in position of the object. That's x2 minus x1, where x1 is the initial position and x2 is the final position, which is nothing but delta x, which is equivalent to delta R I was just talking about a while ago. Now, what is distance? Distance can be defined in two ways. It can be defined as the magnitude of displacement, but this isn't always correct. Let's see why. Or it can be defined as the entire path that's covered by the object. Now, consider a body. It starts at, let's say, x is equal to 5. So let's say its coordinates are 5, 0. And it moves around in a circle, in a parabola, in an ellipse, all sorts of weird paths, okay? And finally, it comes back to its initial position. That's x is equal to 5, that 5, 0 point. Then we say that the displacement is 0 because the initial and final positions are the same. So if I subtract the two, I should get a 0. So displacement is 0, but the distance is not 0. The distance was that entire path that it is covered, the path length. That was the distance. Speed and velocity. Now speed is the ratio of distance to time, and velocity is the ratio of displacement to time. So distance is different and displacement is different, therefore speed and velocity are different. Now in speed and velocity we have average and instantaneous. When we talk about average speed, we talk about the total distance, meaning the whole path length, divided by that time interval. So if I say what is the average speed for the first 5 seconds for the motion of a car, let's say, you're going to calculate how much distance it traveled in those first 5 seconds and divide it by 5. Average velocity, on the other hand, is the total change in the displacement divided by the time. So again, if I take the car example, for the first 5 seconds, you're going to have to check what was the displacement at the end of the 5 seconds and take it as x2, and at the beginning, that's at 0, that's t is equal to 0, that's x1, we don't know what that is. Maybe if it was at rest, it will also be 0. So you can figure that out using a graph for values given. Next is instantaneous speed. So it's like the magnitude of velocity at a particular time. So you're gonna have to calculate what the velocity is and take the magnitude of that, meaning get rid of the direction. On the other hand, instantaneous velocity is defined as you can say the rate of change of displacement, dx by dt. You have to use differentiation and calculate that. Or if you're using a graph, it'll be the slope of the tangent of the graph at that point. If you know calculus, it shouldn't be that difficult to understand. If you don't get it, it's okay, just forget it. You can move on later. in other chapters. So now speed. Speed is a scalar quantity. It has no direction, velocity. It's a vector. It has a direction as well as magnitude. The speed will always be positive. But velocity, it depends on direction. So maybe if it's going to the right side, it's positive. If it's going to the left side, it's negative. If it's going up, it's positive. If it's going down, it's negative. So you get the idea, right? Opposing directions will have different, well, it'll be either positive or negative. So in this case, since we just made this huge difference, that means speed will always be greater than or equal to velocity. It can never be less than the velocity. Next is acceleration. Acceleration is the rate of change of velocity. So instantaneous acceleration, a is equal to dv by dt. Of course, it's a vector quantity. And also acceleration can be positive or negative depending upon its direction. Some people have the misconception that a negative acceleration is deceleration. This is wrong. It is called deceleration depending upon the direction of velocity, which is shown at the right hand side. I'll discuss that in a while. So that means if we have an acceleration in a downward direction, let's take acceleration due to gravity, it's equal to minus 9.8 meters per second. So that's an acceleration, it is not a deceleration. Now uniform motion means that the acceleration is equal to 0. Now if acceleration is equal to 0, it follows that velocity is constant because acceleration changes the velocity. If there's no change in acceleration or there's no value of acceleration altogether, then the velocity remains constant. When this happens, we have some equations. Sorry about that. When acceleration is constant or uniform, on the other hand, it means acceleration has a constant value, like 2 meters per second square or 5 meters per second square. And then we can use these four equations given below. That's v is equal to u plus at, v squared is equal to u squared plus 2as, s is equal to ut plus half at squared, and s is equal to u plus v divided by 2 into t. Now v is the final velocity, u is the initial velocity, a is the acceleration, t is the time interval, and s is defined as the displacement. Hope that makes sense. And you should know units pretty well. You should try to practice what are the units of acceleration, velocity, speed, all that stuff. Then directions. Now let's study two cases. I'm actually working on the right hand side right now. So case 1 and case 2. If acceleration and velocity are in the same direction, meaning that let's say both of them are going to the right side, or both of them are up, or both of them are down, or both of them are going to the left side, then the object will accelerate since both of them are in the same direction. But let's say, okay, so that's called acceleration. What if both of them are in the opposite direction? That's in case 2. So that means velocities maybe to the right side, acceleration to the left, or vice versa, or velocities going up, acceleration is down, or vice versa. In this case, the object decelerates. Like when I throw a ball up, acceleration due to gravity is minus 9.8, it's acting downwards, but I threw the ball upwards, so it has a velocity that's up. Therefore, it will slow down as it goes higher, so it decelerates. So it doesn't have to be that the acceleration is negative. It just means that the acceleration and velocity are in opposite directions for deceleration to occur. Next are graphs. So we have two graphs we usually deal with, the displacement time graph and the velocity time graph. Displacement time or xt graphs work with the displacement in time. As you can see, the slope is actually the change in the y coordinate divided by the change in the x coordinate. So y coordinate in this case is x, so dx by dt. And from what we studied previously, we know dx by dt is velocity. Therefore, the slope of an xt graph is velocity. Then velocity time graph. In a velocity time graph, the slope, once again here, we have v as the y and t as the x. So dv by dt is the slope. And this is nothing but acceleration. So hence the slope of a vt graph is acceleration. And notice that the area under the graph is equal to the distance covered by the body. So that's pretty convenient, something you don't want to forget. Let's work more on graphs. Now, the first row deals with xt graphs, the second is vt graphs. So let's work with 1, 2, 3, which are xt. So the first one, when an object is at rest, you can see that this displacement does not change with time. It's constant. So that means that the object is not moving, it's staying at a fixed position. Next is the uniform motion one. You can see that x is increasing uniformly. That means dx by dt should be constant. The slope is constant. V is constant. If V is constant, acceleration is 0, therefore it is uniform motion. Then third one, acceleration. So there is some change in V, as you can see. Dx by dt is not constant, the slope is not the same. Or if it was, it would be a straight line, but it's not. So when you're actually working with physics, it's helpful to work with math in parallel, so you can always read up more on graphs about slopes if you have confusion on this topic. So actually in the first case there's acceleration, and then in the second case there's deceleration, and you can figure that out using the slope. Next is uniform motion. Okay, so now working with 4 to 6, these are VT graphs, velocity time graphs. So the fourth one, you can see velocity is remaining constant at a value of 4 meter per second. So since velocity is constant, that's uniform motion because acceleration is 0 then. Look at the second graph, not the second, let's say fifth graph, uniform acceleration. So when we have uniform acceleration, you can see v is increasing at a constant rate. What is the slope over here? A. Okay, we have dv by dt. There is a value of slope. In the fourth one, the slope was 0. If you notice, it's a horizontal line, and the slope of a horizontal line is 0. Or tan, if you remember, the slope is equal to tan theta. You can see the angle here is 0. Therefore, acceleration, tan 0 is 0. In the fifth case, we have a value for slope, and it's constant. Therefore, it's a uniform acceleration. In the sixth case, though, the slope is not constant. Acceleration keeps changing, so we have an irregular acceleration, so it's irregular motion. Next is a small bit on relative velocity. Now, this is the velocity of one object with respect to another. So let's take two objects A and B having VA and VB velocities respectively. So let's study different cases. When two objects are moving in the same direction, then velocity of A with respect to B is VA minus VB. So it's like someone who is VA. Let's say the person is A, and they're moving with a velocity of VA. How will they see VB? So it's with respect to them. And then VBA is, let's say person B is moving with VB, and how do they see VA moving? So they're already in motion, so we have to take that into consideration when we make this calculation. That's why it's VB minus VA. So that's when they're moving in the same direction. If they're moving away or moving towards each other, it's more or less the same. When A is moving away from B, it becomes VA minus VB, and when they're moving towards each other, they appear to come faster because both of them are moving, so it becomes VB plus VA. Now the basic thing, even if you didn't really get what I said just now, the basic concept is velocity of A with respect to B is always equal to VA minus VB. The reason why moving away and moving towards have different signs is because the direction of velocity changes, and you can actually trace that. So you can trace that and get an idea of what's going on around here. Now, that's one thing. Then, expanding that concept where I just said VAB is equal to VA minus VB, you can also calculate velocities at an angle. So if I give you vector A and vector B, which represent velocity A and B respectively, I can actually find out VAB first of all by using the triangle law of addition. So now we want VA minus VB. VAB is equal to VA minus VB. We know that. Now we can take it as VA plus minus of VB. So when we make a vector negative, its direction becomes opposite. So notice that I wrote in the first little triangle thing, minus VB. That's the direction of minus VB. But then if you look at the second one, you have plus VB, which is in the opposite direction. So if you really don't get what I'm saying right now, you should do basic stuff in vectors in math. So as you can see, VB is with VA, the head of VB is touching the tail of VA, and the resultant vector is such that the tail of the resultant vector VAB touches the tail of VB, but its head touches the head of VA. So you have to position the vectors in such a way. So then that's how we find VAB. What about VBA? Now VBA will be VB minus VA. So VB, you can see it's positive, but VA becomes negative. Its direction becomes opposite. And then we just position them, and we get VBA. So now notice that VAB and VBA are in opposite directions. So this is how you can actually work with velocities at angles to each other when they're not in a straight line with each other. Hope that makes sense. Thanks for watching.